Several factors can contribute to motor burnout. Circuit protection is important. Was the circuit breaker or fuse sized correctly for the 20 horsepower motor? Overcurrent protection devices should trip before the wire overheats. Wire length and voltage drop could be another factor. The voltage drop along the length of the number 6 wire may have been significant, reducing the voltage available to the motor and affecting its starting performance. Temperature effects are yet another factor. The low temperatures in the unheated shed could have increased the resistance of the wire, further reducing voltage to the motor. Cold temperatures can also increase the friction in the motor bearings, making it harder to start. The motor's efficiency can also contribute. A less efficient motor will draw more current at startup. Motor age and condition are also crucial. An older or poorly maintained motor may have higher starting currents than a new or well-maintained motor. To address these issues, firstly, verify the circuit protection. Ensure that the circuit breaker or fuse is sized correctly for the motor's rated current, which is 59 amps times 1.25 equals 73.75 amps. Secondly, measure the voltage drop. Use a voltmeter to measure the voltage drop along the length of the number 6 wire to determine if it is excessive. Consult National Electrical Code Table 310.15. B16 for voltage drop limits. Thirdly, consider a larger wire. If the voltage drop is excessive, consider upgrading to a larger wire size, such as number 4 copper. Fourthly, install a motor starter. A motor starter can reduce the starting current by allowing the motor to accelerate gradually. This can help prevent overheating and extend the life of the motor. Also, if possible, insulate or heat the shed to reduce the impact of cold temperatures on the motor and wire. When a motor burns out, several electrical and environmental factors can be at play. One of the first things to consider is the circuit protection. The circuit breaker or fuse that's supposed to protect the motor and wiring might not be properly sized for the actual load. If it's too large, it won't trip quickly enough to prevent damage when the motor draws excessive current, especially during startup. The wire size itself also plays a crucial role. Number 6 copper wire has a certain ampacity or current carrying capacity, but the length of the wire run and the voltage of the system can significantly affect its performance. If the wire is too long for the voltage, you'll experience voltage drop, meaning the voltage at the motor terminals will be lower than the source voltage. This reduced voltage can cause the motor to draw more current to compensate, leading to overheating and potential burnout. Then there's the ambient temperature. In an unheated shed, especially in a place like Pennsylvania, temperatures can plummet below freezing. This extreme cold can increase the resistance of the copper wire, further exacerbating voltage drop issues. Cold temperatures can also increase the viscosity of the lubricant inside the motor bearings, making it harder for the motor to start and increasing the starting current. The motor's design and condition are also important. Different motors have different efficiency ratings, which affect how much current they draw for a given horsepower output. An older or poorly maintained motor may be less efficient, drawing more current and generating more heat. It's also possible that the motor windings have deteriorated over time, reducing their insulation resistance and making them more susceptible to shorts and ground faults. When troubleshooting a motor burnout, start by verifying that the circuit breaker or fuse is properly sized for the motor's full load amps, as specified on the motor nameplate. Multiply this value by 1.25 to account for the motor's starting current. If the breaker or fuse is too large, replace it with the correct size. Next, measure the voltage of the motor terminals while the motor is running under load. If the voltage is significantly lower than the rated voltage, investigate the voltage drop in the wiring. Use a voltage drop calculator or consult NEC Chapter 9, Example Number 4, to determine the appropriate wire size for the length of the run and the expected load. If the voltage drop is excessive, upgrade to a larger wire size. Consider installing a motor starter. A motor starter is a device that limits the inrush current when the motor starts. This can reduce stress on the motor windings and the electrical system. There are several types of motor starters, including reduced voltage starters and soft starters. Finally, consider the environmental conditions. If possible, insulate or heat the shed to maintain a more stable temperature. This will help to reduce the impact of cold temperatures on the motor and wiring. Also, inspect the motor regularly for signs of wear and tear, and perform any necessary maintenance, such as lubricating the bearings. By carefully considering all of these factors and taking appropriate corrective actions, you can prevent motor burnouts and extend the life of your equipment. The initial assessment involves confirming that the installed circuit protection, either a circuit breaker or a fuse, is appropriately sized for the 20 horsepower motor. An undersized protection device will trip prematurely, while an oversized one might fail to protect the wiring and motor from excessive current. The calculation 59 amps times 1.25 results in 73.75 amps. This means the overcurrent protection should ideally be rated around this value. Check the existing breaker or fuse to ensure it aligns with this requirement and is in good working condition. Voltage drop along the length of the number 6 wire can significantly impact the motor's performance. Voltage drop occurs because all wires have some resistance, and the longer the wire, the greater the resistance. This resistance causes a reduction in voltage at the motor terminals, potentially hindering its ability to start and run efficiently. To assess voltage drop, firstly, measure the voltage at the source and at the motor terminals under load. Secondly, calculate the voltage drop percentage using the formula voltage drop divided by source voltage, multiplied by 100. Thirdly, consult NEC table 310.15. B16 for acceptable voltage drop limits, which typically recommend no more than 5% for the combined feeder and branch circuit. If the voltage drop exceeds these limits, consider upgrading to a larger wire size to reduce resistance. The cold temperatures in the unheated shed can exacerbate the situation. Low temperatures increase the resistance of copper wire, further reducing the voltage available to the motor. Additionally, cold can increase the viscosity of lubricants in the motor bearings, making it harder to start. To mitigate temperature effects, firstly, consider insulating the shed to maintain a more stable temperature. Secondly, use motor heaters to keep the motor windings warm during cold periods. Thirdly, select motors and lubricants designed for low temperature operation. The motor's efficiency rating indicates how effectively it converts electrical energy into mechanical energy. A less efficient motor draws more current to produce the same amount of work, increasing the risk of overheating. Check the motor's nameplate for its efficiency rating and consider replacing it with a high-efficiency motor if feasible. The age and condition of the motor also play a role. Older motors may have deteriorated insulation, worn bearings, and other issues that increase their current draw and susceptibility to failure. Regularly inspect the motor for signs of wear, such as unusual noises, vibrations, and overheating. Perform preventative maintenance, including lubrication and cleaning, to extend its lifespan. Upgrading to a larger wire size, such as number 4 copper, can significantly reduce voltage drop and improve motor performance. Use a wire size calculator or consult NEC table 310.15. B16 to determine the appropriate wire size for the given load, distance, and voltage drop requirements. A motor starter can reduce the starting current by gradually increasing the voltage applied to the motor. This reduces stress on the motor windings and electrical system, preventing overheating and extending the motor's lifespan. Consider installing a reduced voltage starter or a soft starter depending on the motor's size and application requirements. In summary, a comprehensive approach that addresses circuit protection, voltage drop, temperature effects, motor efficiency, and motor condition is essential for resolving motor burnout issues. Remember to consult the NEC and other relevant standards for guidance on electrical installations and safety practices. To elaborate further on the concept of circuit protection, let's delve deeper into the role of circuit breakers and fuses. These devices are designed to interrupt the flow of current when it exceeds a predetermined level, thereby protecting the wiring and equipment from damage due to overloads and short circuits. Circuit breakers are resettable devices that trip open when an overcurrent condition is detected, while fuses are single-use devices that melt and break the circuit. When selecting a circuit breaker or fuse for a motor circuit, it's crucial to consider the motor's full load amps and the applicable code requirements. The NEC specifies that the overcurrent protection for a motor circuit should typically be sized at 125% of the motor's full load amps. This allows for the motor's inrush current during startup, which can be several times higher than its running current. However, the code also provides exceptions for certain types of motors and applications, so it's essential to consult the relevant sections of the NEC to ensure compliance. In addition to the overcurrent protection, it's also important to consider the short circuit protection for the motor circuit. Short circuit protection devices are designed to quickly interrupt the flow of current during a short circuit, preventing catastrophic damage to the wiring and equipment. Short circuit protection devices can be fuses, circuit breakers, or motor short circuit protectors. The selection of the appropriate short circuit protection device depends on the motor's size, type, and application, as well as the available fault current at the installation location. Understanding the concept of voltage drop is crucial for ensuring proper motor operation. Voltage drop is the reduction in voltage that occurs along the length of a wire due to its resistance. The amount of voltage drop depends on the wire's length, size, and material, as well as the current flowing through it. Excessive voltage drop can cause a variety of problems, including reduced motor torque, overheating, and premature failure. To minimize voltage drop, it's essential to use appropriately sized wires and keep the wire runs as short as possible. The NEC provides guidelines for calculating voltage drop and recommends limiting it to a maximum of 5% for the combined feeder and branch circuit. There are several online voltage drop calculators available that can help you determine the appropriate wire size for a given application. Understanding the impact of temperature on motor performance is essential for ensuring reliable operation in cold environments. Low temperatures can increase the resistance of copper wire, reduce the viscosity of lubricants, and cause condensation inside the motor. To mitigate these effects, it's important to select motors and lubricants that are designed for low temperature operation. Motor heaters can be used to keep the motor windings warm during cold periods, preventing condensation and improving starting performance. Insulating the shed can help to maintain a more stable temperature and reduce the impact of cold temperatures on the motor. Motor starters play a crucial role in protecting motors from damage during startup. When a motor starts, it draws a large amount of current, which can stress the motor windings and electrical system. Motor starters are designed to limit the inrush current and gradually increase the voltage applied to the motor, reducing stress and extending its lifespan. There are several types of motor starters available, including reduced voltage starters, soft starters, and across-the-line starters. Reduced voltage starters use resistors or auto transformers to reduce the voltage applied to the motor during startup. Soft starters use solid-state devices to gradually increase the voltage applied to the motor, providing smooth and controlled acceleration. Across-the-line starters apply full voltage to the motor during startup, which can be suitable for small motors but not for larger ones. The selection of the appropriate motor starter depends on the motor's size, type, and application, as well as the available power supply and a desired level of control. Regularly inspecting and maintaining motors is essential for ensuring reliable operation and preventing premature failure. Motor inspection should include checking the motor windings for signs of overheating, damage, or contamination. The motor bearings should be lubricated regularly to prevent wear and tear. The motor should be cleaned to remove dust and debris, which can impede airflow and cause overheating. The motor connections should be checked for tightness and corrosion. The motor's performance should be monitored to detect any signs of reduced torque, increased current draw, or unusual noises. By implementing a comprehensive maintenance program, you can extend the life of your motors and prevent costly downtime. Selecting the right wire size is critical for electrical installations to ensure safety and efficiency. The ampacity, or current carrying capacity, of a wire is determined by its size, material, insulation type, and the ambient temperature. The National Electrical Code, or NEC, provides tables that list the ampacity of various wire sizes under different conditions. When selecting a wire size, it's essential to consider the load it will carry, the length of the run, the voltage drop, and the ambient temperature. The NEC recommends limiting voltage drop to a maximum of 5% for the combined feeder and branch circuit. It's also important to direct the wire's opacity if it will be exposed to high temperatures or installed in a conduit with other current-carrying conductors. Using an undersized wire can lead to overheating, voltage drop, and potential fire hazards. Understanding the principles of motor control is essential for designing and installing motor control systems. Motor control systems are used to start, stop, and control the speed and direction of motors. They also provide protection against overloads, short circuits, and other faults. Motor control systems can be simple or complex depending on the application. Simple motor control systems may consist of just a switch and an overload relay, while complex systems may include programmable logic controllers, variable frequency drives, and communication networks. Variable frequency drives, or volts, are used to control the speed of motors by varying the frequency of the applied voltage. They can provide energy savings, improved motor performance, and precise speed control. Programmable logic controllers, or PLCs, are used to automate motor control systems. They can be programmed to perform a variety of functions, such as starting and stopping motors, controlling speed, and monitoring system conditions. A thorough understanding of electrical safety practices is essential for anyone working with electrical equipment. Electrical safety practices include wearing appropriate personal protective equipment, such as gloves, safety glasses, and insulated tools. De-energizing circuits before working on them. Using lockout-tagout procedures to prevent accidental energization. Inspecting electrical equipment for damage or defects. Following proper grounding and bonding procedures. Maintaining a safe distance from energized equipment. Reporting any electrical hazards to the appropriate personnel. By following these safety practices, you can minimize the risk of electrical shock, burns, and other injuries. To further elaborate on the effects of cold temperatures, consider the specific properties of materials at low temperatures. Copper, while an excellent conductor, experiences an increase in resistance as its temperature decreases. This increased resistance means that for the same amount of current flowing through the wire, there will be a greater voltage drop. This is because voltage drop is directly proportional to resistance as described by Ohm's law. The increased voltage drop reduces the voltage available at the motor terminals, which can significantly impact the motor's performance, particularly its starting torque. Starting torque is the twisting force the motor can generate when it first starts up, and if it's insufficient, the motor may struggle to overcome the load. Furthermore, the viscosity of lubricants in the motor's bearings increases at lower temperatures. This means that the motor has to work harder to turn the bearings, requiring even more current during startup. This combination of increased wire resistance and increased bearing friction puts a strain on the motor, increasing the risk of overheating and burnout. In addition to these electrical and mechanical effects, cold temperatures can also affect the insulation of the motor windings. Some insulation materials become brittle at low temperatures, increasing the risk of cracking or damage, which can lead to short circuits. To mitigate these cold temperature effects, several strategies can be implemented. One approach is to use motor heaters. These are small heating elements installed inside the motor housing that keep the motor windings warm when the motor is not running. This prevents condensation and maintains the insulation's flexibility, improving starting performance. Another approach is to insulate the shed where the air compressor is located. This helps to maintain a more stable temperature inside the shed, reducing the temperature fluctuations that can stress the motor. Additionally, using synthetic lubricants that are designed for low temperature operation can help to reduce bearing friction. These lubricants remain fluid at lower temperatures, making it easier for the motor to start. From the perspective of motor efficiency, it is essential to understand how motors convert electrical energy into mechanical energy. In an ideal motor, all of the electrical energy would be converted into mechanical energy, but in reality, some energy is always lost due to inefficiencies. These inefficiencies are primarily due to resistance in the motor windings, friction in the bearings, and magnetic losses in the motor core. The efficiency of a motor is expressed as a percentage, with higher percentages indicating greater efficiency. Motors with higher efficiency ratings draw less current for the same amount of output power, reducing energy consumption and heat generation. When selecting a motor, it's important to consider its efficiency rating. Premium efficiency motors, also known as NEMA premium motors, are designed to meet or exceed certain efficiency standards, providing significant energy savings over standard efficiency motors. In addition to selecting an efficient motor, it's also important to maintain it properly. Regular lubrication of the bearings reduces friction and improves efficiency. Keeping the motor clean and free of dust and debris improves airflow and prevents overheating, which can reduce efficiency. Monitoring the motor's performance and addressing any issues promptly can also help to maintain its efficiency. If a motor is operating at reduced voltage due to voltage drop, it will draw more current to compensate, which can reduce its efficiency and increase the risk of overheating. Another aspect to consider is the power factor of the motor. Power factor is a measure of how effectively the motor uses electrical power. A low power factor indicates that the motor is drawing more reactive power, which does not contribute to the output power but still increases the current flowing through the wires. Improving the power factor can reduce energy consumption and improve the overall efficiency of the electrical system. Power factor correction capacitors can be installed to improve the power factor of motors. In terms of preventative measures, regular inspections are paramount. It is essential to establish a routine inspection schedule to identify any potential problems before they lead to motor burnout. During these inspections, pay close attention to the following key areas. Firstly, visually inspect the motor for any signs of damage, such as cracks, broken fins, or loose connections. Secondly, check the motor bearings for any signs of wear or lubrication issues. Listen for unusual noises, such as grinding or squealing, which can indicate a problem. Thirdly, measure the motor winding resistance to identify any shorts or opens in the windings. Fourthly, monitor the motor temperature to detect any signs of overheating. Use a non-contact infrared thermometer to measure the temperature of the motor housing and compare it to the manufacturer's specifications. Fifthly, check the motor voltage and current to ensure they are within the specified limits. Use a multimeter or clamp meter to measure the voltage and current under load. Sixthly, inspect the motor control panel for any signs of corrosion, loose connections, or damaged components. Seventhly, verify the operation of the motor protection devices such as overload relays and fuses. Eighthly, keep a detailed record of all inspections and maintenance activities. This will help you to track the motor's performance over time and identify any recurring problems. In terms of wire size and ampacity, one should consider that the ampacity of a conductor is the maximum amount of current it can carry continuously without exceeding its temperature rating. The ampacity of a wire depends on several factors, including its size, material, insulation type, and the ambient temperature. The National Electrical Code, or NEC, provides tables that list the ampacity of various wire sizes under different conditions. When selecting a wire size for a motor circuit, it's essential to consider the motor's full load amps, the length of the run, the voltage drop, and the ambient temperature. The NEC recommends limiting voltage drop to a maximum of 5% for the combined feeder and branch circuit. It's also important to direct the wire's ampacity if it will be exposed to high temperatures or installed in a conduit with other current-carrying conductors. If the wire is too small, it can overheat, leading to insulation damage and potentially a fire. If the wire is too large, it will be more expensive and may not fit properly in the equipment terminals. In terms of NEC tables, one must be aware that NEC Table 310.15 V16 provides ampacity ratings for conductors based on their size, insulation type, and ambient temperature. This table is used to determine the appropriate wire size for a given load. The table lists ampacity ratings for conductors in free air, as well as conductors installed in raceways or cables. The ampacity ratings are based on the assumption that the conductors will be operating at their maximum rated temperature. It's important to direct the ampacity ratings if the conductors will be exposed to high temperatures or installed in a conduit with other current-carrying conductors. The NEC provides directing factors for various conditions. When using NEC Table 310.15 B16, it's important to select the correct insulation type for the application. Different insulation types have different temperature ratings which affect their ampacity. The most common insulation types are THHN, THWN, and XHHW. THHN insulation is rated for 90 degrees Celsius in dry locations and 75 degrees Celsius in wet locations. THWN insulation is rated for 75 degrees Celsius in both dry and wet locations. XHHW insulation is rated for 90 degrees Celsius in dry and wet locations. It's also important to consider the ambient temperature when selecting a wire size. The ambient temperature is the temperature of the air surrounding the conductor. If the ambient temperature is higher than the temperature listed in NEC Table 310.15 B16, the ampacity of the conductor must be derated. The NEC provides derating factors for various ambient temperatures.